So now we're going to continue on with what we talked about today in class, which is solving limits analytically, which, as I talked about in class, is really the main way in which we are going to solve limits. Graphically and numerically is incredibly useful, and we need to understand that, but we want to be able to do this analytically as well. So, moving on, first we're going to look at some formal definitions of things. This should all be common sense, though. If you understand a limit, this should make sense. These are not things you should memorize. It's just things you should understand. So let b and c be real numbers, let n be a positive integer, and f and g be functions with the following limits. The limit as x goes to c of f of x equals L, and the limit as x goes to c of g of x equals k. Alright, so all this first one is saying is that if I multiply the function by some constant b, then the limit will also be multiplied by that constant b. If I add or subtract the two functions f and g, then the limits will also be added and subtracted when I evaluate the limit at c. If I multiply the two functions, the limits get multiplied. If I divide the two functions, the limits get divided, assuming the denominator is not equal to 0, because we know that does not exist then. And then if I raise the function to a power, then the limit gets raised to a power. Again, these should hopefully be common sense. So, try a few examples of this. Pause the video. Evaluate these limits. Unpause when you are ready to check. Alright, so the limit as x goes to c of 4 times f of x is 4 times 3 halves, because the limit as x goes to c of f of x is 3 halves. 4 times 3 halves is 6. The limit as x goes to c of f of x plus g of x is 3 halves plus 1 half. That's 2. Conveniently, they already had a common denominator. The limit as x goes to c of f of x over g of x is 3 halves over 1 half. I multiplied the numerator and denominator by the reciprocal of the denominator, and I get 3. The limit as x goes to c of f of x times g of x is 3 halves times 1 half, which is 3/4. The limit as x goes to c of g of x quantity cubed is 1 half cubed, which is 1/8. And the limit as x goes to c of f of x over 6 is 3 halves over 6. So I multiply the numerator and denominator by the reciprocal of the denominator, and I get 1/4. Fantastic. Any questions? No? Good. Moving on. So, we talked about this today. Not going to spend a lot of time on it. This is just the formal definition of limits of polynomial and rational functions. So if p is a polynomial function and c is a real number, then the limit as x goes to c of p of x is p of c. That just means do direct substitution. If r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c does not equal 0, then the limit as x goes to c of r of x is r of c, which is p of c over q of c. So again, that's just saying do direct substitution as long as we aren't evaluated in the limit somewhere where the function doesn't exist. Moving on. The limit of a function involving a radical. So if we say let n be a positive integer, the following limit is valid for all c if n is odd, and is valid for c greater than 0 if n is even. Basically, if we have an odd root, we can always do direct substitution. If we have an even root, we can do direct substitution as long as we aren't getting an imaginary result, because we can't have a limit with an imaginary result. Moving on. Limit of a composite function. I want you to pause the video and try this one on your own. I think you can figure it out. I have confidence in you. You're bright. You work hard. You try sometimes. So I want you to try this one on your own. Find the limit as x goes to 4 of f of x, the limit as x goes to 21 of g of x, and then the limit as x goes to 4 of g of f of x. I'll give you a hint. Do these two first. Pause the video. Unpause when you're ready to check. Alright, hopefully you got that the composite limit was 3, so the limit as x goes to 4 of g of f of x equals 3. How do we get that? Well, let's look first. The limit as x goes to 4 of f of x, I can do direct substitution because this is a polynomial, so I don't even have to think about it. Just do it. That equals 21. So then, the limit as x goes to 21 of g of x. Again, I can do direct substitution. This is an odd root. So I plug in 21. 21 plus 6 is 27. The cube root of 27 is 3. So now if I look, well, there's a couple of ways I can do the composite. I can either actually just figure out what is the composite function. So g of f of x is the cube root of 2x squared minus 3x plus 1 plus 6. And then I can evaluate that limit as x goes to 4. So that's what I did here. But I can also see from doing each part separately that if I want to evaluate this composite function, I can actually evaluate the limit of f of x first as x goes to 4, and then take that result and do the limit as x goes to that result, which was 21, of g of x. So it's up to you. You have two different approaches. They're really doing the same thing. It's just more how you prefer to think about it. Next, evaluate the limit as x goes to 2 of 2 minus x over x squared minus 4. Pause the video, unpause when you're ready to check. This one's going to be maybe a little bit trickier. Pause the video though. You got this. Alright, so hopefully you got a value of negative 1/4, but how do we get that? Well, first we try direct substitution, and when we do that we get 0 over 0, which is an indeterminate form. Remember. And then as soon as you get that, then what do? You panic. Oh no. And then we try some algebra because really it just tells us that we're not sure. So in this case, I can factor the numerator and I can factor the denominator. I see that those are going to reduce, so I'm left with the limit as x goes to 2 of negative 1 over x plus 2. Now I can try my direct substitution. I get negative 1 over 2 plus 2, and I get negative 1/4. So then the big question, what happened at x equals 2 in the original function? The original function being 2 minus x over x squared minus 4. Correct. It was a whole. Very good. And we know that the y value of the whole is what we get when we plug in the x value into the reduced function. Remember that? All comes full circle, right? It's like the circle of life. Because life is math, we circled around, just rolling on that wheel. Just rolling. But we want to understand the function does not exist here. So f of 2 doesn't exist, but the limit does. And the limit is the y value of the whole. Spoiler alert, anytime you are doing the limit at a whole, anytime you're evaluating a limit at a whole, the y value of the whole will be the limit. Alright, try the next one. You got this. Pause the video. Unpause when you're ready to check. Alright, so what happened here? Indeterminate form. This time we didn't panic though because we know we can do something. Maybe. So we actually don't know because it's a maybe. But we're not sure. So in this case we factor the numerator, factor the denominator, and then boom. I see you whole. I'm going to get rid of you. So I eliminate you. And then I reduce you. And then I do the limit as x goes to 4 of x minus 1 over x plus 2. Direct substitution. Boom. 1/2. Nice work, team. Next one. Limit as x goes to 1 of x cubed plus 1 over x minus 1. Pause the video. Unpause when you are ready to check your work. Alright, so here, hopefully you got an answer of does not exist. Why is that? Well, again, first, just try direct substitution. That should always be your go-to try. Just try direct substitution, because if it works, that's your answer, and that's the easiest way to do it. But when I plug in 1 here, I get 2 divided by 0. That is not an indeterminate form. That just means it doesn't exist. So then we ask the question, what happened at x equals 1 in the original function? Anyone? Yep, I think who said? Someone said it. I forget. I didn't see who. Someone said it. Yes, but that was correct though. Vertical asymptote. Vertical asymptote at x equals 1. Therefore, the limit does not exist. Next one. This one's going to be a little more difficult. I'm going to see if you can get it on your own, though. Go ahead and try this. Unpause when you're ready to check. Alright, so here hopefully you got 1 over 2 root 2, or if you decide to rationalize that as an answer, which you do not have to, it's up to you, you would get root 2 over 4. So those are the same thing, either of those are correct. How did we get that? Well, again, here we run into the issue of we get an indeterminate form, 0 over 0. Okay, well, what do I do here? Because I don't see like an easy way to factor that. So your big hint is you have the roots in the numerator. So we are going to rationalize the numerator. So remember, as I just pointed out on this problem, rationalizing is not really necessary if you're just trying to rewrite an answer. It's a technique that is very important though. And this is an example of why it's important. So here we are rationalizing the numerator. which means that we are just getting the radicals out of the numerator. So I'm going to multiply the numerator and denominator by the conjugate of the numerator. I do that because then I know the radicals are going to go away. So when I multiply by the conjugate, we end up with the limit as x goes to 0 of 2 plus x minus 2 over x. Remember, do not distribute in the denominator in this case. Over x times root 2 plus x plus root 2. 2 and a negative 2 are going to cancel. And then you're left with x and this x are going to reduce, and so you're left with the limit as x goes to 0 of 1 over root 2 plus x plus root 2. Now I can do direct substitution, so I plug in 0 and I get 1 over root 2 plus root 2, which is 1 over 2 root 2, or root 2 over 4. Next one. Also the last one. Nice. Alright, I want you to try this on your own. Pause the video. Unpause the video, check for work. Check your work, not check for work. Your work. Alright, so here we get negative 1 over 16. How do we get that? Well, again, we started out with an indeterminate form. Okay, so what do we do? Well, in this case, what I notice is that I have fractions in the numerator. I don't like that in general, so I just want to get rid of that. What do I do to get rid of that? I multiply the numerator and denominator by the least common denominator of the numerator. That sounds like a tongue twister, I know. But basically the least common denominator of the numerator is x plus 4 times 4, because the denominator here is x plus 4 and the denominator here is 4. So I multiply by x plus 4 times 4. So when I do that to the first term, the x plus 4's go away and I'm left with just 4. When I do this to the second term, the 4's reduce and I'm left with minus the quantity x plus 4, which becomes negative x minus 4. In the denominator, again, do not distribute. So I just leave this as x times x plus 4 times 4. 4 minus 4 is 0. Negative x over x becomes negative 1. Now I distributed the 4 in the denominator. That part didn't matter. And then at this point, I can do direct substitution. So I can plug in the 0, and I'm left with negative 1 over 16. One thing I want to point out. Notice how my work is on all of these problems. So what I mean by that is I am writing, and I talked about this in class, but I'm emphasizing again, I write the limit every single time until I actually evaluate the limit. If you do not do that, you will lose points. Also notice that I'm not writing just a big run-on equal sign, because they are not actually equal. So it's very important that my work here is vertical. So I'm rewriting the limit and I'm showing each step each time. Did that here as well. This one didn't have any work. Did that here as well. Did that here as well. So you notice a pattern, right? That until you are actually evaluating the limit, you need to write the limit each step of the way, and you should be doing this vertically, not horizontally, because otherwise it's like a big run-on sentence essentially. And also it's mathematically incorrect. And you don't want to be mathematically incorrect. No one likes that, right? When you're mathematically incorrect, you're really being judged mathematically. And if you're being judged mathematically, then really your life is being judged. And that's just gonna lead you down the wrong path. So, finding limits. Try direct substitution. If that doesn't work, perhaps divide out a common factor. If it's a whole, try rationalizing the numerator. Try getting rid of a denominator in the numerator. These are all techniques that you will learn and understand with practice. You talk at practice. Practice. Have a good night.